Lesson 1, all over again. Here we go, guys. So we are starting into Unit 6. Units 6, 7, and 8 are all integrals. Okay, so we have our third big topic. We spent the year in limits, and we talked a lot about derivatives, and now we get to talk about integrals. So that is the direction we're headed. Obviously, the old notes, don't lose them, don't lose track of them, keep them available because, not that you need to be bringing them to class right now, but come AP review time, you'll want to have those notes available. Who knows, you may even want them available at other times, but I wouldn't say they're worthy of carrying to and from class every day. So, okay, so we're going to take a look at the relationships here. And you'll notice here it says we're taking a look at the relationship between the graph of a rate of change function and the area of the region between the derivative graph and the x-axis. Now, I want to point that out because, okay, so rate of change. What is your brain supposed to think in calculus when we talk rate of change? What did we just spend the last however many units going over? Derivative, yes? So when we talk rate of change, that is derivative. Well, the direction we're headed now, area of the region between the derivative graph and the x-axis, area under the curve, this is the idea of the integral. And that is where we are headed this semester. Okay? No, you're not supposed to know what an integral is yet. No, you're not supposed to know anything about it. But every time we talked about slope and rate of change, I need your brains thinking derivative. Now, anytime we talk about area under a curve, I need your brains thinking integrals. Okay? And we'll learn about integrals as we go, but just giving you a little idea. So this first example, kind of looking at area here. In order to avoid flood water entering your home, you rent a pump. Oh, I guess this is about Tropical Cyclone Imelda. So the writer of this curriculum lives in Florida, so tropical hurricanes here. Or cyclone, sorry. Brought more than 40 inches of rainfall over a 72-hour period, although this one was actually in Texas. So, okay, in order to avoid floodwater entering your home, you rent a pump that can remove water at a rate of 500 gallons per hour for the first 8 hours of pumping. As the storm grew stronger, you got a second pump, and for the next 16 hours, you could remove 900 gallons per hour. So 1A, draw a graph that models the removal of stormwater from your property and label the axes correctly. So, what do we have happening here? We have a pump that, what? At a rate of 500 gallons per hour for the first 8 hours of pumping. Well, what do you think this bottom axis is going to be? Hours. Yep, it's going to, and officially I'm going to call it time, but it is going to be time measured how? In hours. Okay, and so if we have time here, what about our vertical axis? Yeah, it's the gallons of storm water, or gallons of water. Okay, so what do we know? For the first 8 hours, here's my 8 hours. For the first 8 hours, we're moving water at a rate of 500 gallons per hour, right? So if we're talking 500 gallons per hour, at 1 hour, 500 gallons per hour. At 2, each hour it is 500 gallons, right? And so we are looking here, for the first 8 hours, 500 gallons every hour. Okay, so at 1 hour, there's 500 gallons. At 2 hours, 500 gallons that hour. Third hour, 500 gallons per hour. And so this piece right here represents 500 gallons per hour for 8 hours.
So it's not the slope?
No. Excuse me. Now, what about the next piece? As the storm grew stronger, you got a second pump, and for the next 16 hours, you could remove 900 gallons per hour. Okay, so what's the next 16 hours mean? That's going to be from 8 hours to 24 hours. And from 8 hours to 24 hours, what are we removing each hour? 900. Gosh. Don't expect straight lines out of me today. Okay, so this big square, rectangle, excuse me, 900 gallons per hour for the next 16 hours. Okay, so that graph models the removal of stormwater. Okay, it's 500 gallons per hour for each of the first 8 hours, and then it was 900 gallons per hour for each of the next 16 hours. If I label axes, I label in terms of words, but this would be my t-axis. I'm going to say g of t for my function here because it's gallons in terms of time. Now, look at question B. You have question B on your paper, and I'll move to the next screen here in a moment. But when we say area under a curve, this represents the area between the graph and the horizontal axis. Find the area under the graph from 0 to 8 hours. And what does this value represent in context of the tropical storm Imelda? So, from 0 to 8 hours. Thoughts on the area here? Yeah, it's a rectangle, yes. So 500 height times 8 wide. And what is 500 times 8? Okay. So 500 times 8 is 4,000. What does that represent?
Total gallons.
Okay. Over those 8 hours, there were 4,000 gallons of stormwater pumped out by the one pump, right? So I have written in my notes, a total of 4,000 gallons of stormwater was removed during the first 8 hours of the storm by pumping. So however you want to write it, but the idea of what that means. Total of 4,000 gallons of stormwater was removed during the first 8 hours. Okay, C when you're ready. Find the total area under the graph for the entire 24-hour period. Explain the media in the context of the scenario. So the total area under the entire graph for the entire 24-hour period. Well, what do we already know? For the first 8 hours, we already know we multiplied 500 times 8 and got 4,000, yes? What else do we need to do?
900.
Okay. The next 16 hours, it was 900 each hour, 900 gallons per hour. And so, whoops, wrong way. There we go. 900 times 16, which was, is it 14,400? Okay. So what about total area? Okay. Add the 4,000 in, and we are at 18,400, if I did my math right. What does that mean?
How much total water was pumped in the 24 hours?
Okay. In 24 hours, there was a total of 18,400 gallons of water pumped using the 2 pumps, right? Okay, so put something in words there so you have it. Total of 18,400 gallons of stormwater was removed in 24 hours. And I'm going to say using the 2 pumps. Eventually, we'll get to a point, like that's a very basic introduction here, because that's area under a very basic curve, right? Very easy to find area of a rectangle. So very easy to find area under a nice flat line here, right? But what happens when it changes to parabolas, other various curves? How do you find the area under the curve? And this is where integrals come into play. Okay, you guys got what you need here? So, today we're going to be talking about something called Riemann sums. And when we talk about Riemann sums, it's going to help us to get not exact, but estimates of areas underneath the curve. So, 2 big ideas in calculus are the tangent line problem and the area problem. So, tangent line problem we've already done a lot of, right? Area problem is our new up and coming. In the tangent line problem, you saw how the limit process could be applied to find the slope of the tangent line or the derivative at any point on the curve. The second classic problem in calculus is finding the area under the curve that is bounded by the graph, the x-axis, and using any 2 x values. So as we talk about this, and a lot of this will make sense as we go through some examples, but area as limits. So in the limit of rectangles approach, we take the area under a curve within a certain interval by approximating a collection of rectangles. So what we're going to do today to kind of begin is we're going to take underneath a curve and break it up into rectangles. And we're going to find the area of each rectangle and sum those up. That's the idea of Riemann sums. Now, we can talk about inscribed or circumscribed rectangles. What's the difference between inscribed and circumscribed? Vocabulary that we need to be familiar with. It's not that you'll see it a lot really in what we're doing today, but it is stuff that could pop up on AP. If something is inscribed, it's where? It's inside something, right? So an inscribed rectangle is going to be under a curve. A circumscribed rectangle, if something is circumscribed, it's outside. And so I'll show you the difference here in a moment, but this is the idea that a rectangle is going to go outside the curve some. Okay? The more rectangles used, the better the approximation, and that's where we'll get into integrals. And when we get to the integrals, the number of rectangles is increased without bound, or so without limit, and we get the area. So that will be our eventual. Again, we're not doing integrals today. So specifically, we're interested in finding the area of a region bounded by the x-axis, the graph, and today we are focusing on non-negative functions defined on some interval. When we say non-negative functions, we're meaning today our functions will always be above the x-axis. They will always be in the positive y value, so it will always be above the x-axis. And yes. Okay. So this example here, okay? Consider a 30-gallon aquarium is being filled with water at a rate modeled by the given function. Okay, R of t equals 6 sine pi over 8t, where t is time in minutes and R of t is gallons per minute. Find the volume of water in the tank after 5 minutes by using 5 rectangles that are 1 minute wide and R of t in height. So as you look at this, we want the volume of water in the tank after 5 minutes. So here's 0, and here we have 5 minutes, right? So these rectangles are representing we basically want the area under the curve from 0 to 5. Okay? Now, are these rectangles precisely all under the curve? No, they're not exact. I mean, these several rectangles go over, right? This rectangle is underneath. But Riemann sums is just an estimation. Okay, it's not going to give us exact. But there's times we need this. So, what you need to look at here is you need to look at, we have an equation, right? And when we have this equation, we also have, if you notice some of these rectangles, every rectangle has a point meets the curve at a point, yes? And those points are important because those points, not only are they a point of the rectangle that's on the curve, they represent the height of the rectangle, yes? And how do we find area of a rectangle? Area of a rectangle, we think what? Length times width, right? Now, I'm going to change that up here a little bit. Instead of length times width, I'm going to say, okay, it's going to be the width of the rectangle times the height of the rectangle. Same idea, right? One dimension times the other. What do you know about the widths of these rectangles? They're all 1. Okay, makes it pretty easy. That will often happen in Riemann sums. What do we know about the height of the rectangles? Well, this height here, of the first blue one, it's a little over 2, but I need more precise than that. This is, the height of this blue rectangle is whatever my function r of t is when t is 1. The height of my red rectangle is whatever my function is when t is 2. My yellow rectangle has a height of, okay, 5.5-ish, but it's whatever you get when t is 3. The green rectangle when t is 4, and the blue rectangle when t is 5. Okay? So we need to go through and find those values, and this will be a calculator thing. We need calculus calculators, though, not physics calculators today, please. What am I hinting at?
Radians.
Radians, not degrees, please. Etta, we go back and forth a lot in here, so. So I'm going to set up a chart to get our information here. What t values am I going to have to plug in? I'm going to have to use t values of 1, 2, 3, 4, 5, right? I don't need 0 because do I have a rectangle at height 0 or at time 0? No. So we're going to use t 1, 2, 3, 4, 5. And then we're going to plug that in to the function. So this is where you get it set up in your calculator, right? And we're doing 6 times sine of pi of 8 times whatever t is. Did we get the first one? I have mine in my notes to 3 decimal places. So remember, AP always wants minimum 3. What'd you guys get the first one to be?
2.296.
Yep. And does that make sense based on the graph? Yeah, that makes sense, doesn't it? Okay. What about when you plug 2 in?
4.2.
Yeah. Okay. Have you found a way to comfortably plug them in on your calculator? This is something where I would get the first one set up, and then I would go up and copy and paste it. The other option is you could plug this, you could graph this, and then plug the values in on the graph. Remember how we've done that? Where you can plug your x values in on the graph. So, okay. 5.543 sound familiar? 6. And shouldn't be a surprise. Doesn't really look like it on the picture, but 5.543 again. And if your parabola is symmetric, that would make sense. Now, I'm going to make a third column here. And this is total area. And again, we'll look at on the next page, next two, I don't know, eventually we'll get to setting up some total Riemann sums. But try and get you guys to think about this. So, the area of the, after one, what is this, minute? After 1 minute is the 2.296. What's the area after 2 minutes going to be? What do we do to get the area after 2 minutes? Add the 2.296 and the 4.243. $6.539 is what mine has. What about the total area after 3 minutes? Yep, 12.082. After 4 minutes? How many of you guys did that on the calculator? 18.082. And after 5 minutes? $23.625. Okay. So the question was find the volume of water in the tank after 5 minutes by using the 5 rectangles that are 1 minute wide. So after 5 minutes, because we've got 1, 2, 3, 4, the 5 rectangles. After 5 minutes, the aquarium has 23.625 gallons of water in the tank. After 5 minutes, aquarium contains 23.625 gallons. Of water. Okay. Now, okay, we'll talk about this more in some upcoming problems, but this is what I would call a right Riemann sum for one. It's a right Riemann sum because where are each of the rectangles touching the curve? On the right side of the interval. Does that make sense? Okay, so because each of these, at each of these points, so like at time 3, when I look at time 3 in the curve, it's there, my rectangle touches on the right. So if I was drawing the rectangle, I'd have to go to the left. Okay, it touches on the right. Each of these touch on the right. We talk about circumscribed versus inscribed earlier. This is an example of an inscribed rectangle because it's totally under the curve, right? Whereas this is an example, these all are example of circumscribed rectangles. Not that they're all outside of the curve, but that they do extend outside of the curve. Okay? So again, we'll talk more, I'll give you more vocabulary knowledge as we go, but try and get you guys some information there. Okay, by using more rectangles with smaller widths, we could achieve a better approximation. In fact, if we considered taking this to a limit of accumulating an infinite number of rectangles, we would arrive at the exact volume of water in the aquarium after 5 minutes. This is called the definite integral. Okay, and this right here is integral notation. Okay, so this is the integral from 0 to 5 of r of t times dt. And so what we want to talk about here is, first of all, the 0 and 5. 0 would be your initial time. Gosh darn it. So what I would call T naught with a T, 0, whereas 5 would be your, I want to say T of 5. No, I don't want to say T of 5. T, it's your final time. So T of F is what I'll say there. Okay. Excuse me. R of T, this piece right here, represents basically the height of the curve. It's the curve, so it represents the height. It's the rate height. And D of T represents the width. So that is the change, that amount of change in T. In this case, the amount of change in T was just 1. Each T value, or each rectangle was 1 wide. And the integral here, it's another way of saying summation. You guys remember summation? We're going to use it some here, but the E there that represents summation, it's the same idea here. This is Roman notation for summation is what it is. So that's again going to represent summing. In other words, adding a bunch of stuff up. As I said, we're not really doing actual integrals today. We're just kind of introducing some thoughts here. Okay. Got what we need there from that page? Okay. At the top of the next page are 3 different types of Riemann sums. Okay. You will notice that on all of these graphs are all the same increasing line. Okay, whether your graph is increasing going up or decreasing going down can make sense, or it can make a difference. But so right here, these are left endpoint inscribed rectangles. So they're left endpoints because on each interval, my rectangle touches the graph on the left side of the rectangle. Okay, so these are left endpoints. If you're ever told to do lower rectangles, and it's not really coming up in this lesson, but it could. Lower rectangles would be putting your rectangles so they are all underneath the curve. And notice my rectangles are totally under the curve, so they're lower for that reason. They're also inscribed for that reason. They are underneath the curve. Okay, so we're going to focus mostly on left, right, and midpoint is going to be our vocabulary. So these are left because they touch the curve on the left side of the rectangle. Does that make sense? I have a hard time knowing how to explain this. And my brain is just obvious, and so I struggle with how to explain this. So I'm hoping it's kind of obvious to you. If not, we'll keep working through it. Okay, so this next piece, these are right. They're right because each of the rectangles touches the line, the curve on the right side of the rectangle. These are what we would call upper or circumscribed because they go above the curve, which in this case is a line. And then the fun ones, midpoint. Notice, where does my rectangle touch the curve? In the middle of the rectangle. Okay, so a little more challenging there, but those are the 3 different types. There's a picture for reference. We will work to understand that a little bit better. Okay. Definite integral definition. So, looks like a mess, doesn't it? But let me explain at least a little bit of it, and the more we work with this, the more you'll learn. So, let f be continuous on the interval a to b, and the function f of x be greater than or equal to 0, so that's just saying the function is positive, so assuming the function is above the x-axis for all x in the interval. Let the interval a to b be partitioned into n subintervals. So that's taking that interval from 0 to 5, and earlier it was breaking it up into 5 intervals, right? Whatever the case is. So into n subintervals of equal length, and equal length being that delta x. So delta x can be found by doing B minus A, B and A being the endpoints. So like earlier, 0 and 5 would have been my endpoints. N being how many subintervals there would be. So if I go back and use the one from earlier, that we didn't have to find it, but A would have been 0, B would have been 5, and then this is 5 intervals. And so it helps you to know that, okay, 5 minus 0 divided by 5, each interval is 1 in length, is what it's saying. So that delta x, in this case it'd be delta t, helps you find how wide each interval is. Sometimes it's obvious. I mean, here, 0 to 5, 5 intervals. That was obvious. Sometimes it's not so obvious, and this idea is very helpful. Okay? Then, the definite integral of f over the interval of a to b is given by this. Now, this right here is the integral part that we will use. This is what I already talked about, where it's the interval from a to b of f of x times dx, where f of x, that's your function. So like here, it's the line or it's your curve. That represents the height. D of x represents your width. Okay, so that's d of x is another way of saying delta x, change in x. Okay. Now, here's the fancy limit notation. Limit notation says the limit as n approaches infinity, the sum from k equals 1 to n of f of c of x delta x. And the idea here that f of c of x represents your height, delta x represents your width. Okay. I'll be honest, you're not going to see this limit notation much. We're going to go for the more refined integral notation. But this is saying, okay, the limit from 1 to however many intervals there are of the function times the width, adding them up over and over. Okay? Okay. As we get ready to go into this example here, general solution method for inscribed or circumscribed rectangles, basically, a suggestion of steps in a way, things to think about. One, you're going to want to have a picture, okay, draw a rough graph of the function over the interval. Use what we talked about a moment ago, that formula to determine each subinterval length. So how long is each subinterval? So doing b minus a divided by n. Compute x coordinates of rectangles at either left or right hand end. So figure out when you draw your rectangles in, whether they're, left hand, right hand, but which x values you're using. Compute the areas of each rectangle. So that's plugging those x values into your function. And then find the summation. So summing them up. Now, I mention all of this and hold these thoughts because we'll use those on the next page. Okay. Example 3 here, notice what it says. Find the area under the graph f of x equals this function on the interval 0 to 5 using what? Geometry. So don't think calculus for a moment. Think geometry. So what are we doing here? The interval from 0 to 5. We want the area under the curve. So from 0 to 5, I want that area. What shape is that? It is a quadrilateral. It's a more specific quadrilateral of a trapezoid. Can you see the trapezoid? Turn your head sideways. Right? Can you see the trapezoid? Because what's a trapezoid have? When you guys think of a trapezoid, what do you think? Whoops. That's what you guys think of it with the trapezoid, right? Well, what is this one? This is, let's see. That's not very good, but okay. Do you see the trapezoid here? Now, because it is important to upcoming problems, because we're going to talk about the trapezoid rule also, how do you find area of a trapezoid?
1/2 B1 plus B2.
How do you know that?
Did
you have flashcards for Christmas?
No. Yeah.
Did you actually?
No. Megan.
How?
I just break it.
Okay. Now, and this is, I was waiting for someone to say that. Is there the other option of breaking this into a rectangle and a triangle on top of it?
I did.
Yes, there is. However, I need us to review the area formula for a trapezoid because it's going to be important in upcoming examples. So, I'm forcing us to go trapezoid. Sorry. We need to. So, I wrote it as 1/2 times height times B1 plus B2. Ethan said 1/2, and he had the height at the end. It doesn't matter ultimately, right? I've also seen it written as h over 2 times B1 plus B2. I've also seen it written as B1 plus, or h times B1 plus B2 all over 2. You know, there's lots of different ways we could write this. Now, with this in mind, okay, what do we know here? What are my bases?
5 and what other side?
Well, your base is 1, and then it's going to be f of 5 for your other base.
Okay, so remember bases are the two parallel sides, right? So where are my bases? I have base 1 down here and base 2 here. So bases on a trapezoid are always your parallel sides. Base 1 is going to be 1. Or, how about if I say it this way? Base 1 is whatever the function is evaluated when x is 0. And what is my function when you put in 0? 1/2 times 0 plus 1, it is 1. Or you can tell by looking, this has a height of 1, yes? Now, what about this one? What is base 2? I mean, we could say approximately 3.5, but is it that exactly?
Yes.
How do I know? Okay, so f of 5. In other words, take 5, put it into the function, and you'll find what that point is, right? Half of 5 is 2.5, plus 1 is 3.5. Or if you prefer, 7/2. I guess in my notes I have 7/2. Okay, and what is the height of this trapezoid? This many. I need a better answer than this many. I like Maddie's finger answer there. The height is what? It's a distance between bases. Has to meet those bases at a right angle, yes. And so the height is 5. Okay, do some math. 1/2 times 5 times 1 plus 7/2, or 1 plus 3.5. So 1/2 times 5, I'm going to say 5/2. 1 plus 7/2. So 7/2 plus 2/2 is 9/2. 5/2 times 9/2 is 45/4. Or 11 and 1/4, 11.25. Okay. And this is area, so officially we could say units squared if we needed a label. Okay. Yes, you are seniors. You're in calculus. You should know area of a trapezoid. As opposed to thinking Ethan is crazy for knowing it, you should know it. So join him in knowing it.
He is crazy.
Now go to your flashcards, Ethan.
Okay, so we are going to look at a couple of different problems here. Oh, I forgot. This is the day that needs red and blue. Okay. Red, blue, or pick two colors. Whatever.
Okay.
I forgot.
I have colors. You got colors?
If you're a colored pencil type person, there are colored pencils here. I think I got crayons out last time, didn't I? Red and blue, whatever two colors you want. I mean, I just change it and circle whatever color I'm using, so. Okay, so what we're going to be doing here is we're going to look at these problems, and we're going to look at them in a couple different ways and kind of compare, okay, if we use left-hand sums versus right-hand sums. How different is our answer? Which is a better answer? Overestimate versus underestimate. Being able to determine if something is an overestimate versus underestimate is important in AP. So, for the function shown at the right, draw rectangles forming the left-hand sum, and officially it says do this in blue. I would do it lightly, whatever you do, because here's the deal. On this same graph, we're also going to draw in right-hand rectangles in red.
Oh.
Me doing this on the BenQ is going to be, I'm probably just going to have to erase. I don't even know. We'll see. Now, okay, so left-hand sum, that means my rectangles all touch the curve on the left side of the rectangle. And it says that what? Delta x is 2. What does delta x represent again?
2.
But what is it?
Oh, the distance.
Okay. It is the width. So we're going to draw rectangles in that have a width of 2. So that means my first rectangle is going to go from 0 to 2, if that makes sense, right? And it's a left-hand rectangle, which means how high is it going to go?
To the left side.
Left hand of the rectangle has to touch here, wherever that curve touches. So there's my first rectangle. So it is touching at what appears to be 8. And we don't have a function here, so it is 8. Okay. My next rectangle is going to go from 2 to 4. It's a left-hand rectangle, so where does it touch the curve? The left hand of the rectangle at 2 is going to be here at 7. So we're going to have a rectangle that looks like that. Are you seeing this? Where's my next rectangle? What height does my next rectangle have? I agree. Do you see it? Because my next rectangle, it has a width of 2, so it goes from 4 to 6, but it's a left-hand rectangle, so it is the height of the left side of the interval, so it's whatever the height is at 4. So those are the rectangles for a left-hand sum.
You don't have to do the last one.
So I'll be honest, I don't like this picture very well, because it does look like we should keep going, doesn't it? But when I looked at the key, they didn't keep going. So I'll be honest. Technically, yes, you should use every little piece. So I'd prefer this better if it ended at 6, but we're just going with it, okay? So valid point, valid question. Now, calculate the left-hand sum. So I'm going to note this. This is a left hand with 3 rectangles. So that's left-hand sum with 3 rectangles. So I said LH sub 3. Okay. What do we know about the first rectangle? What about the area of the first rectangle?
16.
Because it was, I don't want to hear 16 yet.
It was delta x2, and then it went up to
So
f of 0 was 8.
okay. So it had a width of 2, height of 8, yes? So that first one, I don't know that I want to try and write them here. I'm going to write it just up here for my reference for a moment. That first one was 2 times 8. What's the next one?
2 times
7. Okay. 2 times 7. And what's the last one?
2 times 5.
2 times 5. What do you notice about all 3 rectangles? They all have a common width, yes? So, common to see Riemann sums written is we're going to put the 2 out front because they all have the same width, yes? And then we're going to add the heights of 8 plus 7 plus 5. Mathematically, it's the same. In other words, we could have taken 16 plus 14 plus 10. For this particular problem, that'd be easy peasy, right? Okay, when you get a problem that is more difficult, has decimals, has many more intervals, you won't want to multiply them each out and then add them. Okay, it will be easier to say, okay, 8 plus 7 plus 5, which is 20 times 2. And we'll get the same answer. Does that make sense what I did there? Assuming I did. Did I do my math right? Okay. Now, I guess we'll get to it on C. I was just going to ask if this is an overestimate or an underestimate, but we can go ahead and talk while my picture isn't messy. 40 is the area under this curve using a left-hand sum. Is 40 an overestimate or an underestimate? It's an overestimate, right? 40 is more than what the answer is. We don't know what the answer is, but we know it's less than 40 because all of my rectangles are outside of the curve. So I'm going to go ahead and write it here because I think it's helpful to talk about right now. Okay, switch to red. Next, draw the rectangles that represent the right-hand sum. Shade them in red and calculate the approximate area under the curve given by our right-hand sums. So I guess I was supposed to shade mine, but if I shade mine here on the VinQ, that's ugly. So you can shade if you want, but mine would not be readable. Okay, now we still have the same widths. There's still going to be widths of 2. So we're still going to have a rectangle from 0 to 2, 2 to 4, 4 to 6. Okay, right-hand sum. So the rectangle from 0 to 2, how high is it going to go if it has to have be a right-hand sum? Because on the right hand of the rectangle, which is at 2, yes, we're going to go up to this, which is on the right. I don't know why I made that solid up there. But that's a right-hand sum because the interval 0 to 2 touches the curve on the right-hand side. So that's going to be 2 by 7. What about the rectangle from 2 to 4? How high is it going to go? It's a right-hand sum. So on the right hand of the interval at 4, where does my graph touch at 4? And it touches at 5. So that's going to be a 2 by 5. What about your next one? You guys see it? From 4 to 6, on the right-hand side of that interval, my graph touches at 1. So that's going to be a rectangle that is 2 by 1. So this is our right-hand sum, done in red. So I'm going to say the right hand of 3. Each width is 2. This time the heights are 7 plus 5 plus 1. So that's going to be 2 times 13, which is 26. What do you know about 26?
That's really small.
It's too small, isn't it? Again, we don't know what the answer is, but I know 26 is I know 26 is an underestimate because all three of those rectangles were under the curve with room to spare, yes? Okay. C we've already answered, haven't we? Which sum overestimates, and that was our left-hand sum. Which sum underestimates, that is our right-hand sum. Okay. Now, I am going to point out this graph, this function, it was a decreasing function, yes? You know what I mean when I say decreasing? Do you remember? The graph is going down, right? So, note for future self, or for future, which that future is going to have to be tomorrow, this is a decreasing function. Okay? We'll talk about it for tomorrow. What about this function we're getting ready to talk about? What kind of function is it? This is an increasing function, isn't it? Whether your function is increasing or decreasing will play into whether a sum is an overestimate or underestimate. Okay? D, repeat steps A through C for the function shown, except this time delta x is 0.5. However, they also have the graph spread out. Well, okay. We can start talking about this. I have a feeling I'm going to have to finish this up tomorrow. Awkward ending spot. But okay, so delta x, 0.5. I'm back to using blue for my left hand. Okay. And so 0.5. So from 0 to 0.5, left hand. Gosh darn it, I drew too much in there. How tall is my rectangle going to be? Yes? So don't pay attention to what your teacher's doing there. That's going to be 1 because right there. 0.5 to 1. How tall is that one going to be if we're talking left hand? It's going to go up to 4, isn't it? So you're catching on maybe? 1 to 1.5. How tall is that one going to be? 6. Okay. So this was 3 intervals again. What is my width each time? 0.5. What are my heights? 1 plus 4 plus 6. So what does that make my left-hand sum? Half of 11, which is 5.5. And is that an under or overestimate? Based on how I drew my rectangles, it is an underestimate. It didn't ask, but I guess it did. It will ask. Now, I probably don't have time for right hand, do I? Okay, right hand. The key is how tall are they from 0 to 0.5. This one now is going to have height of 4, yes? Maybe I'll draw them and not say them, let you guys. I want you guys to be able to process this. Are you finding them? So they all have a 0.5 width again. This time my heights were 4, 6, and 7. And the half of 17 is 8.5. And that 8.5 is an overestimate. Okay, I kind of finished that. Sorry, guys. Okay. So we will pick up, we have 5 and 6 to do tomorrow. I would like to think those won't take the whole time, but they'll take a little bit of time. So homework is not due tomorrow. You can probably look at a little bit of it. I know. So disappointed. Although we'll really get into the heavier stuff tomorrow. So maybe you don't know enough to get started too much.